when it first released, when it first took to the skies rather, it was one of the most technologically advanced aircraft ever to take to the skies on Earth. And the actual technological advancements that were created in order to push it to the limits it did were great and honestly have not been exceeded since. So we wanted to really analyze the ins and outs of the Concorde specifically and compare it to a more standard conventional wing off a Boeing 747. So beginning. Apologies for that. So beginning, significant variation exists in aircraft design, and contrary to where a lot of wind tunnel analysis happens here, instead of focusing specifically on one dedicated aerofoil setup, we're going to look more into full-scale wings, full-scale being size to the wind tunnel that we have. And also importantly is that the methods of lift generation can differ greatly between these wings and their different aerofoil setups, shapes, and profiles and sizes. And that's one of the things that we'll really analyze closely when looking at the wing of a Concorde versus something more conventional like a 707, which hence our project objective. Our project, you'll find, was very wide in scope and hands-on application, however very narrow in actual applied objective. We are specifically looking at a very conventional jet passenger narrow-body airliner compared to a Concorde. Moving on. So we had a methodology applied. Beginning, we had to develop the CAD of 2 separate wings. This was done using SolidWorks modeling software. The models were created to fit as large as they could within the wind tunnel. We had an 18-inch wide wind tunnel here at Kettering University, and in order to get the best and most applicable and realistic lift drag values, we wanted to make the wings as big as they could. So we selected quite an odd scale for this. It was 1 to 46.5, hence we had to do some custom manufacturing to actually get the wing sizes we need. But what this meant is that the relatively very wide 707 wing was at the absolute max width it could be in the wind tunnel, whereas the much more narrow Concorde wing would be fit to scale with that 707. We also wanted to test pressure taps compared to the lift and drag. For the sake of brevity of this presentation, we'll be mostly looking at the lift and drag outputs, as there is a lot of good data that we pulled from that. And what we found is that actually the lift and drag that we found for these 2 wing setups was actually very conducive to what we'd expect to see on the real full-scale airplanes. And yes, then calculate the drag coefficients, and eventually in our full report we will be comparing to full-scale aircraft and as well in this presentation our expected results. Okay, so why do we choose this project? We wanted to help solidify our understanding of wind dynamics. It's easy to say from a textbook, well, when a wing increases its angle of attack, you generate more lift at the cost of more drag, but actually seeing it applied in a wind tunnel with a lift and drag device is a bit of a different scenario to help solidify that in our heads. This also allows for greater analysis of the lift effects on the Concorde wing, which has a very unique way of generating lift at both low and high speeds, and we'll talk more about that in just a second. Finally, personal interest. As we said earlier, all of us have vested personal interest in this project as it goes. So, about aerofoils, I'll keep this relatively brief, but aerofoils basically operate on the principle of differential pressure. We have a lower pressure generated on the underside of the aerofoil, a higher pressure generated on the underside of the aerofoil, and a lower pressure generated above, and the resultant force is a lifting force which we generate. The air has a tendency to stick to objects. It has viscosity, much like oil, water, anything of that sort would. That produces drag. You can see, lift from shear stresses, disrupted, skin friction drag. The frontal profile area, that's the projected area, which we'll talk more about as we get to our testing methodology. That also generates actual friction at the stagnation point at the front where velocity is 0. Now, to start with, the Concorde's very interesting, but we need a baseline. So we're going to look at the Boeing 707 to begin. This is a subsonic-oriented aircraft. It has a maximum speed of 627 miles per hour. This is a first or second generation, depending on who you ask, narrow-body jet airliner meant to carry a large amount of passengers over a great distance. And the wing was actually quite complicated compared to a conventional aerofoil for testing. We have a 7-degree upsweep, there we go, and a 35-degree sweep back, which is somewhat complicated to actually model, hence we went for the construction method we did using a segmented monocoque design. We'll get more into that as we go. Continue on. The actual ins and outs of the 707 wing, specifically one to use in order to create a solid baseline. This model is applicable to a wide range of other aircraft. The 707 first took to the skies well over 50 years ago, and to this day it remains one of the most widely sold aircraft in the world in terms of commercial aviation. It was a smash hit by all accounts, and some of them still fly today, albeit in different use case scenarios. The U.S. Air Force still uses them as aerial tankers and things for aero refuelings. But yes, also relevant information on both of these wings is very readily available, which is very helpful for trying to create CAD and compare to real patterns. Now, the Concorde itself, a supersonic-oriented aircraft that generates lift in a very different manner from your standard aerofoil-based aircraft. This is a max speed of Mach 1.77, though some modified have been known to go over Mach 2, I believe it's Mach 2.04 specifically, which is about 1,354 miles per hour. The Concorde was so fast at its release that a person could celebrate New Year's Eve in London, hitch a ride on a Concorde, and celebrate New Year's Eve again in New York and watch the ball drop. Other uses include a team of research scientists at some point wanted to analyze a solar eclipse. They mounted all of their research equipment onto a Concorde and flew it in the path of the eclipse, and they actually managed to keep up with it, which is very impressive, especially for an aircraft that large.
Right.
The wing profile is very interesting. It is specific only to this aircraft. It's a modified delta wing shape. Delta wing effectively being a modified triangle shape. It's called an Agawal wing, which basically is thinned out and stretched even further to improve low speed efficiency and ability to fly. And this is what's so interesting about the Concorde is actually its wing. It has very specific flight characteristics that only exist on the Concorde. So if we actually take a look at this model wing here, at flat, when the aircraft is inclined at a 0-degree angle, the wing is actually mounted in a vertical incline. The lift on a 707 wing, it generates quite a lot of lift at 0, which we'll see from our results. But a Concorde wing generates most of its low-speed lift by getting enormous, quite frankly, angles of attack. The takeoff angle, which is pretty much the most extreme angle you can expect on a 707, is 11 degrees. A takeoff angle on a Concorde is over 18, which, if you factor in the actual angle that's mounted on the aircraft, is over 20 degrees from the horizontal, which is very impressive. Which is part of how it actually generates lift, by using these specialty lift characteristics. Certain other supersonic aircraft do this, but none to this scale of applied speeds. There are obviously certain fighter aircraft and things that do this, but they aren't to this weight. So we will be looking more about how these results pan out in our final wind tunnel testing, but for now I would like to hand it over to Noah. A huge amount of our project was spent putting together these model wings for testing in the aircraft, and he will be going over our construction methodology.